Hello and welcome. Today we'll be talking about OAM light and its applications to quantum information. Since the invention of the laser, scientists have been able to make them do some pretty weird stuff, like changing the color of a laser beam, generating optical interference, and even creating 3D projection sci-fi holograms. But another exciting thing that can be created with lasers is donut beams. No, not this kind of donut. This kind of donut beam. They are called donut beams because of a phase singularity at their center, making them look like donuts when observed face on. I will take this chance to remind everyone, never look into a laser. Ever. Just don't do it. These phase singularities come from the beam having a helical wavefront. The pointing vector, direction of energy, of these waves is skewed because they have an azimuthal component. The pointing vector is what informs the momentum of the field, and because of the skewedness, these fields have orbital angular momentum, OAM, hence OAM light. The degree of angular momentum describes the pitch of the corkscrew of these beams. These OAM light beams have many interesting quantum traits that make them potentially very powerful tools for quantum information processing. Let's start with some basics. Photons carry something called spin angular momentum, which comes from circularly polarized light. Because of the strangeness of the quantum world, it can only have angular momentum of plus h bar or minus h bar. In the crazy Hilbert space, that is quantum mechanics, these spins are orthogonal to each other, and a total spin state can be written as a superposition of these spins, with associated coefficients that inform the probability of measuring each respective spin. Because this is a two-state system, and it's quantum, we call it a qubit in quantum computing. However, in donut beams, photons have another interesting quantum property, orbital angular momentum. OAM is unrelated to the polarization of the photon, and so it is a completely independent property and distinct from spin. This angular momentum is also quantized. However, unlike spin, it can have any integer value of h bar, both positive and negative. These OAM states are orthogonal and can be written as a superposition. But because there is a potential of n orthogonal states, when used in quantum computing, this degree of freedom is called a qnit. Because it has more states, a qnit can carry a lot more information and is potentially a useful tool for things like quantum cryptography, where a lot of information needs to be processed extremely quickly. Via a nonlinear optical effect called spontaneous parametric downconversion, two photons can become entangled in both their OAM and polarization. Entanglement of both of these degrees of freedom is called hyperentanglement. Hyperentanglement is very exciting because it allows us to encode more information when we entangle particles. Because we can encode a lot of information in just a single particle, we can do quantum operations on it. But in order to start computing, you need some gates, specifically C0 gates. Researchers have constructed these for light, and they show that standard quantum processing can be done on just a single particle. Specifically, two gates are very useful for this, a P-C0 gate and a OAM C0 gate. Can you guess what those stand for? A quantum NOT gate requires a control and target qubit to operate. Luckily for the photon, OAM and spin can be treated as separate qubits, and this can be achieved for single photons. I will be denoting spin states with plus and minus, and OAM states with 0 and 1 for the remainder of this presentation. A polarization-controlled NOT gate, PC0, uses the value of the polarization of the photon to switch to the value of its angular momentum. When the polarization is in a plus state, it will flip the value of the OAM, and when it is in the minus state, the OAM will pass the gate unaffected. A second gate does the exact opposite. The OAM-controlled NOT gate, OAM-C0, will flip the values of the spin polarization when controlled. Clever combinations of gates is fundamental to how computers operate, and clever combinations of these quantum gates can allow us to do some pretty amazing things with just a single photon. Remember how I mentioned the photon can be hyperentangled? Well, we can use this trait to do entanglement swapping, with the creatively named swap gate. Let's imagine we have two photons, photon 1 and photon 2, denoted by the subscripts 1 and 2 respectively. At point A, they are in a superposition of OAM states, entangled with a polarization state. We can then operate this state on a PC0 gate to produce the state at location B. Remember, a PC0 will flip the value of the OAM if the photon is in the plus state. We will then operate the state on a OAM C0 gate to produce the state found at location C. Remember, this time we are flipping the value of the polarization for each photon if that photon has OAM of 1. Finally, we will operate the state C on the PC0 gate once again to get our final entangled state. We can rewrite this in the form we started with to see exactly what is entangled with what. You can see we have now effectively swapped the entanglement. Amazing. So what does this all mean? OAM can be created using classical and modern optical methodologies and have been generated in labs for decades. Because of the ability for a photon to act like a qubit when utilizing its OAM, it has the possibility for a wide range of applications, specifically to fields requiring high-density information transfer. Furthermore, quantum gates have been built to take advantage of hyperentanglement and entanglement swapping, which are the first steps to utilizing these elements for quantum computing. There was a lot of information that we went through today, and I hope you learned a lot. Remember, stay curious and stay smart. This is Thomas Horning, and I hope you enjoyed the presentation.